Welcome to Automated Visual Software Analytics. This part is about software dependability. It motivates automated visual software analytics and shows how it can be applied and why it should be applied. Software dependency refers to the fact that our society, our private life, our economy depends to a more and more increasing degree on the availability of software systems. First, we will look into what are computer-based systems, what do we understand by this term, and then we will ask what about the system dependability. Most likely you are all familiar with a number of computer-based systems. For example, classical applications, desktop applications, big IT systems, or with embedded systems, typically are not visible at all. For example, this is what most people associate with the term computer-based system, machine code. However, systems evolve. Nowadays, computer-based systems are everywhere. For example, they are built in operational systems by means of embedded systems. For example, in the fields of energy or in the field of transportation, logistics, or infrastructure network management, software definitely plays an essential and crucial role. Also in our daily life, as a consumer, as a citizen, computer-based systems are everywhere. Social network communication, for example, is based on a number of globally available services we are all familiar with. These services, to a significant degree, shape the way people communicate. More and more, we are dependent on the availability and usage of such services. There's also a trend, a tendency we can observe that computer-based systems more and more become seamlessly integrated on the one hand, and on the other hand, they become invisible. For example, in the fields of augmented reality, user interfaces and reality blend into each other. Or in the fields of semantic web, we have a large number of progress that allows even to extract meaning from information. Another key trend represents the Internet of Things and ambient intelligence, when computer-based systems become integrated with our daily and regular environment. All these directions can be summarized by pervasive computing or ubiquitous computing. These are the key trends in the next decades. There was a visionary article, The Computer for the 21st Century by Mark Weiser, who states the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. Yes, this somehow summarizes the importance of software systems. Underlying all these technologies are computer-based software systems that are defined to a significant degree by software. So developing software, having a certain quality level, more and more becomes the essential task and challenge in the fields of engineering. This is summarized by the expression system dependability. If software systems are key factors, key elements of complex computer-based systems, we have to ask, what about their abilities and qualities? Key abilities and qualities include, for example, availability. To which degree is the system ready for correct service? Also, reliability represents a key quality criterion. Is this service, this correct service, continuously available? And how can we measure to which degree the service may fail or may be unavailable? So the reliability becomes an essential criterion as well. Also, safetiness is a big issue, the absence of catastrophic consequences on users and the environment. Integrity is another criterion, the absence of improper system alterations, and a more organizational related fact, how can a complex system be maintained? What about the maintainability? The ability for a process, software development, to undergo modifications and repairs. The degree to which our society already depends on systems that show these qualities is incredible. For example, in our daily life, we have a number of examples, communication services, smart home electrics, or operational systems. Most prominently, however, are key developments such as the Mars robot or autonomous cars. This is where most of us see how we depend on software and how software drives our daily life. The consequences, however, are dramatic. Deficiencies of computer-based systems directly start to interfere the operation of our businesses, the way we handle problems, and the way we live in daily life. Increasing risks, in particular in terms of total failures, become crucial issues in the development of computer-based systems. Examples you can find almost every month in the newspapers, at least the big ones. For example, airbag software bugs recently caused to recall large numbers of cars because a installed software was programmed in such a way that it can come to the wrong conclusions while driving a car. Newly installed trading software, another example, where software glitch cost trading firm, it caused a large damage in a short time frame. So this shows somehow how we depend already on these systems and that system dependability becomes a major issue. All this is also realized by software engineers, by software and computer scientists. For example, Bjarne Stroustrup, the inventor of C++, in a recent interview said, "We should aim for a greater degree of professionalism." Highlights this. In software development, there are things in our society that must not break, and most of them depend on software. And we need to consider our system as a whole. Languages and their tool chains are part of it. We need to look into how we educate our developers and how we put emphasis on reliability. So this professionalism refers to the key question, is it really engineering, software engineering, or it's still a kind of experimental approach? And emphasis on reliability. How can we ensure the key properties of software systems? To summarize this chapter, many systems look, as Grady Butch said, dangerously fragile. The bad news is they are fragile. This is another force that will lead us to the next era of how we build software systems. How can we systematically build software systems and ensure the key qualities? Complex computer-based systems, of course, provide a large number of challenges for their planning, construction and management. One key issue is system dependability due to the general and increasing software dependency in our society. Now, how does automated visual software analytics refer to all this? Automated visual software analytics focuses on complex computer-based systems, not on trivial ones, not on small ones, on big system developments. In particular, on the software-based components. And the goal of automated visual software analysis is, among many different objectives, to enable software development teams to handle tasks, budget, risks and quality in a much better way than it is possible today. So software analytics aims to assist developers and all stakeholders in the process of software development to achieve a high degree of dependability in key software qualities. Yeah, this concludes this part on software dependency. We have defined what we understand by computer-based systems, and we have looked into the different aspects of system dependability. Finally, I would like to briefly give you an overview of key terminology introduced in this part. It was the term system, a collection of components organized to accomplish a specific function or set of functions. Of course, it has also an intuitive meaning. Complexity, the degree to which a system or component has a design or implementation that is difficult to understand and verify. So these are the two properties. How can I understand a system? It's difficult or not? And how can I verify how this system is composed? So this refers to complexity. Now we can combine both and we have complex systems. Software, most of you know what software is. Formally, software is defined as computer programs, procedures, and possibly associated documentation and data pertaining to the operation of a computer system. All these definitions are taken from the IEEE glossary of software engineering. Now, the key terms of this part as we define it: a complex computer-based system is a system that is non-simple with respect to its software and hardware components, their structure and organization, and that is difficult to explore, analyze, comprehend, and visualize for humans. The system dependability is defined by a measure of a system's availability, reliability, and its maintainability. It covers all these aspects such as availability, reliability, safety, integrity, and maintainability of a system. And it can be affected by, it's mostly affected by faults, errors, and failures, and other forms of degradation of the software quality. There's also a more unsharp term, software dependency, which basically relates to the fact that almost all segments in private life, economy, and even politics are considerably and increasingly coupled with the dependability of complex computer-based systems. So make sure that you understand these terms and that you have a brief definition for yourself, because the next parts will rely on the usage of these terms as it is defined here. Further reading, I can recommend this article you easily find in the internet from Mark Weiss. It's a computer for the 21st century. And I also would like to draw your attention to an interview with Grady Booch. Modern society relies on dangerously fragile software. You can Google for it and you will find these articles. Let me come to the final remarks, the informal part. We have sometimes synonyms. You will find them. It's called software-intensive systems or software systems, even systems of systems, or just complex systems. We refer to all these different variants to as complex computer-based systems. And also I would like to repeat that the fundamental cause of complexity of these systems results from the software. Hardware, in a sense, can be handled by clearly defined and systematic engineering procedures. Also, it's a big challenge to produce faster and faster and cheaper hardware, but in a way, the hardware process can take advantage of existing engineering principles. In contrast, the software-based part are still much more relevant for the question, how can we define a reasonable approach, reasonable techniques, methods for an engineering-like handling of their development. We will learn more about it in the next chapter.